Thank you very much. I'd like to thank the organizers for the invitation. My talk, I will not be able to say everything, but I will be talking about using some rigorous techniques for trying to at least contribute into this effort of data assimilation. So I will start with the questions how to make weather forecast. Everybody knows of this picture somehow. I'm assuming at the moment that I have a perfect model. U is the unknown, and I would like to find the solution. So I have some observation measurements, and then from the observation, so this is the background flow. This is the observation, then you do some analysis, and then you continue. This is the picture that people have in mind when you do data assimilation. So the point is that in data assimilation, if I assume that I have a perfect model at the moment, and trust me, I can do with errors, okay? So be patient with me. So let's start from chapter 1, as we say. Okay, I have a perfect model, and what's missing is the initial data. So what's the idea here? I'm using some ideas from feedback and nudging. And the word nudging, everybody says, oh, nudging has been around. There's many ladies called nudging. So everybody called nudging different nudging than nudging. And I searched in the literature, and I didn't find the nudging that I'm going to talk about that. Usually they nudge observation to the full solution and not to the projection of the solution in the space of observation. So it's a completely different idea of nudging. So the idea is we combine the model measurements by adding some feedback control terms to the equation. So you have the original model, and the reference solution is missing. The initial data of the reference solution is missing. So I take the original model and do some approximation. Namely, I take the original model plus some feedback through the nudging. And then from here, I will get some approximation. But then I need to initialize this approximate solution. Since the initial data is missing, things better be nice. So I'm going to initialize it arbitrary anyway, no matter what. And then I'm going to show that the feedback control approximation system converges toward the solution, the reference solution. This is basically the big picture that I'm trying to show. And let us roll from here. So where this idea, at least for me, where it came from, I was not born doing data assimilation. Where it's coming from, however, I was born or basically mathematically, in a community in which they were working on the Navier-Stokes theory. And then trying to connect whatever we do with turbulence theory, communicating with physicists. Conventional theory of turbulence knows that the instability in turbulent flows occurs at large spatial scales. And I will show you that in a minute. And that there are finitely many degrees of freedom in the flow. So the instabilities occurs at the larger scales, and the viscosity is stabilizing the small, finer scales. So there is a fight between instability from the nonlinearity, but only at the larger scales. Why? Because when the scale is becoming finer, the viscosity takes over. So therefore, you have finitely degrees of freedom. And the idea for many people in applied analysis in the mathematical community was, can we develop a rigorous mathematical framework to understand this picture? Okay? That's basically how things started. And indeed, what are these degrees of freedom? I mean, there was not really specified. And the first rigorous result in this direction, using rigorous approach to the dynamical system, was a work of Foyash and Prodi, in which talking about determining, finitely many determining modes. And what's the idea? The idea is the following. Imagine that you have two solutions in infinite dimensional space of the Navier-Stokes equation, in the phase space. So like two airplanes are flying. Now, if you have two airplanes flying and you project down and you see the airplanes getting closer, you know that the airplanes are not going to hit each other. However, if they are projecting on the low Fourier modes of two solutions with Navier-Stokes, and if you take enough modes and you see that the projection is getting closer, the solution getting closer. This is the result of Foyash and Prodi. So it says the following, that let Pn be a projection operator on the first n Fourier modes, and n is large enough depending on Reynolds number. We know it explicitly. This is some of the theorem. let U1 be two solutions such that the low Fourier modes are getting closer as time goes to infinity. Conclusion, the solutions must get closer. So one can say from this result that the first Fourier modes, n Fourier modes, determine the solution in a unique fashion. So one can think about the first Fourier modes are the degrees of freedom. They have minds of their own. And the other infinitely many modes will follow suit. They cannot have mind of their own. This is the first result in this direction from 1967. Okay, now, of course, we do not measure Fourier modes. However, we measure the fluid at certain points and so on and so forth. Can one really go into something more specific? And the next result was by Foyash and Timam, and then later by Jones and myself, where we got estimate, talking about nodes. What does it mean? Imagine that I have the world, and I'm a news agency, I'd like to know what's happening in the world. You divide it into countries of comparable in size, and at every country you put a reporter. Doesn't matter where you put a reporter. Suppose the solutions of the Navier-Stokes at these nodes, two solutions getting closer at the nodes, then the solution getting closer everywhere, which means the values at the nodes determine the solution in a unique fashion. Once you understand what's happening here, and in the case of Fourier, any numerical analyst tells you what nodes is related to finite differences. Modes like spectral theory. Can you do it with finite elements? Can you do it with other things? The idea is the same. The whole idea is the resolution, the size of the resolution. What's the size of the country that I have? And it doesn't matter which method you take. Therefore, one can talk about general interpolants. One can talk about finite volume elements, or you can talk about a general interpolation like finite elements and so on and so forth. And if you know the solution projected at these larger scales, then it determines the solution in a unique fashion. This was the result from many, many years ago, because from the 90s. And then came the idea of, can one use this information, because these reports is like the observables, the observation, can now one use it to reconstruct the solution? The theorem says that the solution determined uniquely, but there is no method to construct it. Can we use it to construct it? And this is, in some sense, intimately related to data assimilation. Can I recover the solution from this idea? And the idea is basically, I'm going to focus on the Navier-Stokes equation, two-dimensional. Why two-dimensional, not three-dimensional? Because we don't know about the global regularity of the 3D Navier-Stokes yet. If somebody proves it tomorrow, we have lots of papers to be published. They are waiting in the drawer. All what you need is to push the button on the printer, and then you start how many papers. The theory is there. What's we're missing is this piece of the puzzle, namely global regularity of the Navier-Stokes equation. Okay, so that's why I focus on the 2D, because we have global regularity. So this is the equation that I have in mind with the forcing term. So I'm assuming at the moment there's no model error. We have theorems with model errors. And I'm going to talk about continuous in time error-free measurements. Again, it's an assumption at the moment. Again, I will allow to relax these conditions. So what's the idea? This is the approximation model. It's exactly the Navier-Stokes. The black part is the Navier-Stokes part. However, I am adjusting beta IH. IH is interpolation. You gave me the nodal values, for example. I can construct an interpolant operator from that, from numerical analysis. I can approximate by step functions, whatever is your favorite method. I call this IH. So IH of U is the observation that you gave to me. IH of V is part of my algorithm. I add this term, divergence of V equal to 0. Many people in the previous nudging, things with I digged in the literature, they put here V, because they didn't know or were not understood, or they are not a PDE guy, or solving evolution equation which involving some crazy operator in the unknown, IH of V. But nonetheless, this is the equation. So this is the nudging part where I push the larger scales together. Now, if I try to see what happens in this case, okay, so I look for the difference between the two solutions, then the difference satisfying this equation. Now, I do some simple manipulation. I add beta u and subtract beta u, I get this left-hand side and this right-hand side. Notice now what happens. In the left-hand side, if we forget about the right-hand side, I have diffusion, it goes to 0. I have instability coming from the nonlinear term, this bad guy. But this bad guy has two parts. It's destabilizing small scales and larger scales. The larger scales will be killed by the beta, which came from the nudging. And the fine scales will be killed by the viscosity. And what about the rest? The rest will be error, which we will show eventually will go to 0. So let me now summarize what happens. If I looked at this equation, one can assume that the interpolant operator is a good approximation of the identity. So it is small where h is the scale of the resolution. And as an example, one can take IH to be the low frequencies in the Fourier case. Or one can, for example, in finite volumes, if I divide the domain into countries, say squares, and then I look for the local averages, so this is the size of the country H, and I look for the local volume averages, and then I take as an operator to be approximation by step functions. Another option, if I don't want the error to be IH, I can look for nodal values. This will be the error in the approximation. I take, for example, the nodal values, I divide into the countries, and every country I put a point, and then I can approximate the function by local values. These are the kind of interpolant that I am using. So what happens now, this is the theorem that we have with Azwani and Olson. It says if beta large enough, namely you damp or you put nudging strong enough, and if the size is small enough, you need to resolve the scales that basically the theory tells you that you need to resolve, then the conclusion is that V minus U converging exponentially fast with the exponent beta. Now, somebody can say, why can't I take beta to go to infinity? Why can't I take beta to be super large? And now let me give you the physical. Of course, there is a theorem which puts the conditions. But what's the physical motivation? Why I cannot do that? The problem is the following. While you are trying to stabilize the largest scales, because you don't do the stabilization perfectly, I took IH and interpolant. You know, when you walk, you're trying to move your house, like your chair, your table, it's a big object. You have to be careful not to touch the fine objects. So while you are stabilizing the larger scales, the nudging term is making some perturbations of the finer scales. And they are magnified by beta. Now, these are supposed to be killed by the viscosity. And therefore, you have a game now between beta, if it's too large, has to be determined by the viscosity. That's why beta cannot be too large, okay? Unless you would like to take H to be very, very small. So that's where the idea is coming from, that you have this kind of like constraint and you cannot go with beta. Now, so what is the point that I would like to make here is the following. U is solutions of Navier-Stokes, and everybody was talking about chaos. So it is a turbulent solution. So the equation of motion is the Navier-Stokes. Small perturbations can lead to Lyapunov exponents which are positive, and therefore it's bad. However, what this result tells me, if I look at the V equation, at the approximate equation, no matter how I started, first of all, U is exact solution of it, if I start with the right initial data, but any initial data converges to U, which means the equation, the solution of the equation V, which is U also, is stable, globally stable. And this is a very important point to keep in mind for what I'm going to talk about. So U is chaotic with respect to the perturbation of Navier-Stokes, but the V equation has solution U, and it's globally stable. And this is very important for what I'm going to talk about later. Now, some other related work. So once you do an idea for Navier-Stokes, you can do it for other equations. I don't know how to do 3D Navier-Stokes, but I can do 3D Navier-Stokes where I have global existence like alpha models. Then there's some other work with porous medium equation, and then the surface quasi-geostrophic equation. Now, what if I talk about the Bénard convection, because we would like to connect more with physical situation. So I have the temperature and the velocity. The state variables are the velocity and the temperature. However, what we can show, if you give me the velocity, if you know the velocity exactly, I plug it into the Bénard convection or Boussinesq equation, immediately I recover the temperature. And therefore, you ask the question, do I need to observe the velocity and the temperature? And the answer is no. It's enough to observe the velocity and you recover both. And this is a theorem. But then at the same time, you say, well, but I have the incompressibility condition. Div u equals to 0. Do I need to observe both components of the velocity? The answer is no. It's enough to observe one component. Okay? Of course, we wish if we can have a theorem which says, observe the temperature, recover everybody. For Boussinesq, it is not correct. We don't know how to do it, but we have some evidence that's not doable. But for other models, and that's basically what Michael mentioned earlier, I will talk about it in a minute. So for 2 de Bénard, only velocity is enough. This is a result with Farhat and Joly. Then in 2D Navier-Stokes, one component of the velocity is enough. This is a result with Laudancin and Farhat. And then in 3D plantar-geostrophic, when I talk about larger scales, then the temperature is sufficient. And this is basically what was mentioned by Michael Gill. This is what we call the Charney conjecture, that if measurement of the temperature is sufficient to determine all the state variables, namely the velocity as well as the temperature. In 2D Bénard, only horizontal component of the velocity is sufficient. This is 3D Bénard in porous medium, only the temperature is sufficient, and this is basically also result with Laudancin and Farhat. All right, so there are some other work in which people proved that in different norms for different kind of like models. There's some numerical work. I'm not going to talk about computational work. There is not enough time to show everything, but we really implemented this algorithm. Now, the theorem demands that you have to have a very, very fine resolution. For example, for giving Reynolds number, maybe I need to have like 5 million points. That's what the theorem says. However, for this particular case that requires by the theorem 5 million points, we can show that 49 points is sufficient, 7 by 7. And we have some numerics which is really supporting that, and so on and so forth. So there is a lot of work in that direction concerning computations, and there's some computation with the Bénard convention with this group, as well as basically we talk about discretization in time and in space, and that's what I would like to talk about. Now I'm going to move and then talk about discrete in time data assimilation. So far I gave you that the observation is continuous in time. But usually the measurements might be coming discrete in time. So if the measurements are discrete in space, that's what we did, and discrete in time, so I discretize this time and space, what I will do, I need to require that you have to do it frequently enough, okay? And then even imagine that the measurements has some error at the end. So I took the measurements and I construct from that error. What can I prove? So approximate model will be exactly as is. I just put it as is, but now I have some error term. What I put in my model is, in my algorithm, all this quantity because I don't know the separation. But I know in principle there's error and there is real thing. So what's the result that we have? Under these assumptions that I'm approximating the identity, so the following exactly as we did in finite volume, etc., result with Foyash and Mondairi shows that if the error is uniform, E, this is the error in the measurements, and again, if beta is large enough and kappa is small enough, the frequency, then you can show that the lim sup of the error between the reference solution and the algorithm is of order E. So therefore, if there is error in the observations, then there is error in the result, but this is and the difference here, if the error is 0, we know that this is going to 0 exponentially fast. Now, how about the numerical approximations? So let us remember, the solutions of Navier-Stokes are unstable. You have turbulent flows. And therefore, if I do any numerical method, like Galerkin method, you do error in the initial data, because you approximate the solution by projection on finitely many Fourier modes. And as a result, the solution of the Galerkin and the solution of the exact equation, after a while, they will be like exponentially divert in time for short time. But the solution of my algorithm is stable. And therefore, this tells you that, aha, if I do Galerkin approximation of my algorithm, namely I implement it computationally, I would not have this problem. Because the Lyapunov exponent is negative. I have a solution which is U, and it is globally stable. And therefore, this is calling for a theorem. which basically tells you that the error will be uniform in time. And indeed, this is the situation. So I would like to find estimates in the error between the two solutions. So I'm looking, this is the equation that I said I am having. This is the algorithmic equation. And now, if I look into eigenfunctions of the Stokes operator, because I'm doing Galerkin approximation, but the same result work in other contexts, and I will talk about that in a minute. So I look at finite dimensional projections. So when I look for the Galerkin spectral method, so Vn is now the solution of the Galerkin approximation of the algorithm. What we can prove, this is basically the picture. I don't have much time to explain this picture, but this is the exact solution, and this is the solution of the projection of the approximate solution. We know that the difference with these go to 0, but now there is error because of the Galerkin procedure. So here is the result with Mundaini. Again, if beta large enough and h small enough, there is a data which is less than 1 such that Vn, now this is solution of Galerkin, minus the reference solution, the difference is converging exponentially fast with an error which is uniform in time. So I don't have, because now the Lyapunov exponent is negative, so I have uniform. Therefore, if I implement the algorithm computationally, I don't need to worry that it does not really doing the right job. Now, I don't want to talk about post-processing Galerkin because I don't have time, so I will skip that. This is the post-processing part. I don't want to talk about it. So what happens this is the result I just basically mentioned with the post-processing. So I'll just basically to mention something now. What happens if you discretize in time? We have a new result with Ibdah, my PhD students, and Mundaini, which is similar results, discretization in time and space, in which we can show uniform error in space and time for the algorithm when they converge to the exact solution. And in the context of finite elements, because not only Galerkin eigenfunctions, we have the same result with Garcia, Archia, and Novo. One final comment, because people talk about ensemble and talk about probability and so on and so forth. Now, once we have these exact solutions, and where I also showed there's errors as well, there's control on the errors, we can do the same with particle method using this algorithm. If you give me like ensemble of observations, I can take an ensemble of initial data of the V's. They are all converging, and therefore you can lift the probability exactly by the same algorithm, and it's converging at exponentially faster. And since the time is over, I probably will stop here and say thank you.
Thank you very much for this very, very nice talk. Questions? Yes, please.
For the Rayleigh-Bénard case, where you are non-homogeneous, do you have a way also to guess an optimal distribution of your countries, of your measurements spots inside the flow, or you always put them in a homogeneous way?
No, I basically do not know where action will take place in advance. And therefore, I have to be fair. For example, if I would like to divide the world, you know there is nothing happening in the Sahara. So why should I send a reporter? Yeah. But what if today happened to be the hottest ever in the Sahara and you want somebody to report it to you? Yeah. So because I don't know a priori what's the flow and what's happening, so therefore I have to be fair and I divide the domains uniformly or comparable size. And that's the size H. And H plays a role in all my estimates.
So your estimates could be in some sense improved if you know something a priori about the distribution of your flow, and you could maybe improve them by putting less probes, in the smartest places.
Yes. The estimates are depending on the gradient of the solution, which is a priori estimate for it. So if you tell me better, I can do better. And in fact, as I said, my theorem requires, for example, I need 5 million points. But in practice, 49, between 49, like 50, and 5 million, there's orders of magnitude. This shows that basically the algorithm in practice doing much, much better what we can prove about it in theory.
So the upper bound on the coupling parameter on beta was in terms of a certain h, and this h is the quality of the approximation, is the quality of the
resolution. This is h.
The resolution of the
the data. Yes.
Yeah. The resolution of the identity, basically.
Yeah. No, the resolution of where you collect the data.
It's the I of h. It was always called I of h.
H is the size of the countries. That's where you basically resolve the observations. You know, I mean, maybe in the future, everybody will be a walking observation with your laptop or your telephone or whatever. Therefore, h can be like 10 to the minus 1 or 10 to the minus a millimeter. The smaller the h, the better, because you have more and more and more data. But my point is now I'm constrained by how much observations I have. And therefore, h is given. I cannot play with it. I can play with beta. And I can play with the viscosity? No, because the viscosity of the fluid is given. So therefore, I cannot take beta too large because h is given.
But if you measure in Fourier, you could take beta very large, right?
No, 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 no.
Well, I think so.
Well, you can think whatever you want.
If you measure in Fourier, if you measure in Fourier, you can send beta to infinity because you don't touch the small scales. Your input is only on the large scales.
Yes, but the instabilities, let me tell you, the instability from the nonlinearity is exciting small scales and larger scales. And therefore, you need to do something to neutralize that. So either you rely only on the viscosity, and therefore you need to take h too small, or you have to rely on the beta. So it's the whole thing is coming from the nonlinearity. Nonlinearity is exciting everybody, large and small. But the small are killed by the viscosity, and the large are killed by the beta. And if the beta is really too strong, it might really do some damage for the other ones.
So for reaction diffusion, I can tell you numerically, it stops working if you take beta too large. I mean, both the theory and also the numerics, I mean, I know it's only one particular example, but it stops working.
Supplying data in Fourier or in the information space? In Fourier.
Yeah. But as Titi, as Edris was saying, a finite dimensional approximation, finitely many modes.
Michael.
Very nice talk,
Thank you,
Edris. Thank you very much. Since you did refer to my opening talk, there was another point towards the end of it that had to do with just how much observation and how much data assimilation. Since your h is related to your cap n, okay, the number of modes,
Yeah.
in principle, you should be able to estimate the number of observations that you need. Remember that I also said you don't need more observations than something. So I didn't see that you had really estimates for that, but maybe I just missed it.
I didn't give the explicit estimate. Oh, actually, here it is. You see, lambda k, well, I mean, let's go one earlier. So here's h is smaller than this number. L over h is the n. Should be bigger than this number. So this gives you some relation how many modes you need in terms of Reynolds number and so on and so forth. This is part of the theory. I wasn't specific with the numbers, but you are right, 100%. As I said, the whole thing was motivated by the fact that there are finitely determining parameters of turbulent flow to begin with. Yeah.
Last question.
I was just wondering if your results about observing velocity only for Rayleigh-Bernard extend to the primitive equations.
Primitive equations, we have similar results. It is a little bit complicated for the primitive equations. For the velocity, yes, but not for the temperature. Yes, for the velocity, yes, but not for one component, two components because I'm in 3D. So I need two components because the third one is coming from there for free. Yeah, but that's all what I have.
So thank you very much, Edris, for this very nice talk.
Thank you very much.